Hi, in this video I want to demonstrate Docker Compose. Up until now the videos that we've shown are showing you how to set up a database or how to set up a website, whether it was Nginx or .NET Core, and running that in a Docker file. And you could see that you had a website, you had a Docker file, you would build it and run it. Now the only difference that we've got here is that instead of using .NET and the name of the DLL to run it, I'm actually just running a shell script. And that gives me a little bit more power. Because what I can do in this shell script is I can do things that would be a bit more trickier within a Docker Compose, within a Docker file. I can set the environmental variable for the port that's being read within ASP.NET Core. So I can control the port that this container is going to be listening on. That's something very useful if you want to push up to cloud, and that's why I've got it in there. But it's also quite useful within a Docker Compose environment. Now, each one of these sites is the same. You've got the app, you've got a Docker file, so they're all pretty much the same rudimentary thing. The only slight difference is that they're chained. Docker A calls Site A calls Site B, and Site B calls Site C. So these are chained. When I make a call to an hello endpoint, this is going to make a call to Site B. Then, as you guessed it, Site B is going to make a call to Site C, and then Site C is actually going to make a call out to an external system, a GitHub repository to pull some data back. So you can see that this is a chained dependency. Now, I'm not going to get into the nitty gritty of why that's bad. The best microservice is a single separate standalone microservice. However, of course, there are scenarios where you're going to want to call out to another microservice. Just be very careful in doing so. Make sure that there's a legitimate known reason and that the answer to that problem isn't to swallow up that microservice. Like if Site C is only making that call and nobody in the world is using Site C apart from Site B, then Site B and Site C should be swallowed together as one system, as one microservice. One microservice is not one unit of work. It's one concept or business rule or philosophy. There is no real true definition as to how far you want to go. Get that out of the way. That's not what this tutorial is about. This is just about understanding Docker Compose. So just imagine that there's legitimate reasons why these apps are running. Now you can fire these up independently. You can do Docker build and then Docker run for site A, go into site B and do a Docker build, Docker run, and as you've probably guessed, we can go into site C and do a Docker build and a Docker run, and then call site A and hope that site A calls site B and calls site C. But there's more to this app. There's might be a database, there might be a Redis cache, there might be other things that we need to set up. And also, when we start coming into systems like this, we need to think about um, what happens if Site C goes offline? What happens? Do we trace it? How can we track it? How does Site A know where Site B is? And how does Site B know where Site C is? We're not going to be able to control the IP addresses when it goes on the cloud. We're not going to be able to control these things. So we kind of need some way of discovering where the service is so that the sites can see it. And we need some way of being able to trace the conversations happening between these different microservices. So this is where something like Docker Compose can really come to life. Because Docker Compose gives you a contract of how your collection of microservices should be built. So within my Docker Compose, I'm saying, look, let's have Zipkin. I want to be able to trace traffic going from site A to site B to site C. Zipkin is awesome for that. Not going to go into it. You can tutorial it yourself. Look it up online. I might do a video at some point, but that's not what this is about. Consul, I need site B to know where site C is, but I can't hardcode the IP addresses in because that ain't going to work when it goes onto the cloud. Well, Consul is a service discovery system. When an app fires up, it registers itself with the Consul engine And also it can then query the Consul engine to work out where Site C is. So we can use a really nice name, Site C, but that actually then comes back with an IP address from Consul and then maps through. So now we haven't got this statically typed, even domain names. These are just names. I could call it sites XXXXX if I wanted to, if we were building something like that, but we're not. But we could put that in. So that's Consul, and then Redis is just a caching system that we want to use in this platform. And then we're getting into our apps. And what we're saying is that Zipkin, well, there's a Docker image for that already. So let's just use it. Consul, there's already an image for Consul. We can just pull it down from DocHub. Redis, yep, we already know there's a cache for that. But Site A is unique. So what I'm going to do is I'm going to say, right, Site A, the build environment is actually in /Site A, which is that. So now it's going to look for an image inside of Site A, see that there's actually a Docker file in there, and build it for us. And Site A's image then will be built from Site A's Docker file. This is awesome because you can chain together all of these apps with just a few lines of YAML. So Site B, that's just the name I'm giving it. I could have actually called it Site XXX, and it's going to go and get its config and its build from Site B, and it's going to run it on port 5001. Site A is on 5000, and as you've probably guessed it, Site C is on 5002, and they're all running their app. So now, within maybe a few seconds, I can do Docker compose up, and you'll see Zipkin starting. You'll see Site 1 starting, Site 2, Site A, sorry, Site B, and Site C, and you'll see data from Consul. If I go to Bash and see if I can query this. So you can see now I've made a call to Site A. It's gone and it's made a request to Site A. That's made a request to Site B. Then to Site C. But how did they know where they lived? In other words, how did Site B know how to connect to Site C? What name did it use? What IP address did it use? So the answer is it used Consul. And Consul is a way of being able to register a site. So you can see here we've registered Site A. Now I've run this a couple of times, which is why we've got a few error messages. I've run Site A two times now. So there's one that's up and healthy and one that used to be up, which is now dead. If I go into it, we can see that I have got this now instance running, and this is healthy. I can actually connect to this node and work out what to do with it. I can use this now um, as my running app. So now, whenever I want to connect to Site A, I can just use the easy name of my Site A. When I call that in HTTPS, it's going to work out from Consul where to actually go, where does Site A really live, and pull that data back. And same with Site B. You can see Site B, I've had 3 instances of this running. There's only one now that's live. So when we connect to Consul, it'll go, oh, by the way, you can have this. It's also a very cool way of doing load balancing, because imagine if you did fire up 20 instances of my Site B, they would all register with Consul, and therefore Consul would do the round robin and load balancing for you. It is really cool. So what about the calls? I'm making a call here to hello, but how do I know that this is actually really working? What's the trace through? Well, that's where we can use a tool called Zipkin. And Zipkin allows you to monitor the traffic. It allows you to work out what's going on. And we can see here that there was a call from Site A, and we can see the chain. We can see Site A got a call to Hello World. It then made a call externally to port 5001. Port 5001 was Site B. It got this call. and it made a call out to 5002, and that was picked up by Site C. And Site C then made a call out to this GitHub repository to pull some data back. Now we can see what's going on. We can also see that it was, actually Site C that took vast majority of the time up. Nearly, well, let's call it 400 milliseconds of the 441 milliseconds in total. Now you can see that each call is taking a little chunk out of the time. They're all taking their own maybe 10, 15 milliseconds. So you got to be bloody careful when chaining microservices, because before you know it, the time wasted is just in HTTPS calls. Now, of course, you can use different protocols. You can use binary, you can use better handshaking methodologies, socket-driven stuff and things like that, so that there isn't this heavy TCP/IP handshake that you get with a HTTPS or HTTP call. For microservices internally, just use HTTP. No need to use HTTPS. You can keep it secure within your own network. So let's have a bit of a play about with this. What I want to do is I want to kill Site C just for fun. So let's stop it. And it'll take a while for that to stop because it knows it's supposed to be part of this stack of work. So it's trying to work out, right, what you're doing. So that's stopped. If I now run this, I may get a completely different response. So I did get a response, which is, it wasn't a 500 error. So there was actually a response back. And more worryingly, if I look at the response back, I even got a 200. So I got a success. So clearly the developer, which is me, didn't do his job properly because this didn't succeed. Look at the response. It's buggered. It didn't make a call out. So let's go and have a look at our services. Right, we can see now that there's 3 down for Site C, and they're all down. There isn't a working version of Site C now. So it stopped that traffic from happening. But if we look at Zipkin, and if we go back to Zipkin's main screen and do a search, we'll see that there was a call, and we'll also see that there was a failure. So we can see now that there was a problem making that connection out, and you'll be able to see the actual stack trace and any problems and where it happened. So now these errors that were hidden because of stack tracing, because of using multiple microservices to call other microservices, it's visible now. Now, the only tool that I haven't got within this demo is some kind of circuit breaker. However, I was showing it before that the app is running, the app is returning data. It's a little bit slower than it was because it is hitting that error. Now, if you think about it, this remains operational. We're hitting the hello world and some response is coming back. So it's not broken, it's just not doing the original feature it was designed for. I know that sounds really weird to say, but say imagine you hit Netflix's main screen and it goes away and works out the algorithm and works out what your top favorite programs are, and that comes back and populates that list. If for some reason it wasn't able to call that algorithm or couldn't do it in enough time, should Netflix be down? Should that screen be blank? Should it show an error message? Or should it default back to some good state? Maybe there's a popular list in the UK and it knows you're in the UK, so it just delivers that to you instead. And that's what's happening here. In the Because I wasn't able to connect to Site B correctly because Site C was broken, I'm just going to return the response back from Site A and say that everything's okay. However, I'm having to work out whether it's down at the moment, so I could implement some kind of circuit breaker. Now, Hystrix is a thing which has this flick, and it's a circuit breaker like you'd expect in electronics, in that when it's open, you can query site B, but when it's closed, you can query site B, but when the circuit breaker's open, you can't. The connection's off, which means that it knows site C is off. So instead of even trying to connect to it, it will just instantly return the happy default. But it's warning us and it's telling us through Zipkin and through Hystrix that there's an error with one of the services. Site C, there's something wrong with it, guys. Go away and have a look. Now, the error that we're getting is with Site B, but we can quickly see that actually, when we dive into Zipkin, the problem isn't Site C, it's the fact that Site B can't connect to it, but that's obviously because Site C is offline. So it gives you enough to quickly identify the problem, and you solve that problem. You can then quickly fix it and release or update that that Docker image and just redo a Docker compose up, and instantly that system comes back up. And then when you call it, you're back up and running again. Within a few seconds, that service will be live and Site C will spring to life, and you'll have a healthy endpoint that's ready to serve traffic to the rest of the system. Zipkin will then be happy, telling you that all of these connections that have been happening are happy and good, and that you've got this nice chain. You can then look and monitor all of the traffic and work out what is the data, how is data flowing through the system, and make sure that your microservices aren't getting over engineered. You haven't got a spaghetti system, you've got more of these like a family tree type order where you can see data just going out and coming back. What you should never see in microservices is a spaghetti junction where site C calls site A and so on and so on. That's just deadly. But all of this, to get to the point now, all of this was set up within seconds of just doing Docker Compose up. So if I go back now to Visual Studio, Visual Code, and go back and just terminate this, you'll see that Zipkin will close, that Consul will close, that Site A will shut down, Site B and Site C, until eventually the whole cluster is offline. And I can be making changes to all of these systems whilst this is running. I can set it up so that I can build and that each image will look at its volume and take it from site. So you'll have lazy reloading of all of these systems. So you don't have to even keep stopping and starting Docker Compose. It can just run. And then these are deployable images that's been created. These images then can be pushed up to production and used in a production environment without any work. Just take it, drop it out, fire up Consul, fire up Zipkin. Maybe you want a professional version of Zipkin and Consul. You have them maybe hosted as special services within Azure. Then all you need to do is register that with the environmental settings and point it at the appropriate place, and instantly you're up and running. So that's how Docker Compose allows you to compose an orchestration of systems. It's not for just what you can do just one Docker image, so you can just get that up and running quickly, but really it's for creating this orchestration of many systems and just being able to get it up and running very quickly. In the world of microservices, where it's quite common for one service to have 4 or 5 other services as dependencies, that can get annoying and that can get a pain to set up if you're doing it by hand. And it also needs knowledge. Another developer doesn't need to have knowledge. They just need to be able to run Docker Compose up to be able to get this up and running. No longer do developers need to be able to configure servers and set, in this case, 5 Linux machines up and running. all talking to each other, all configured, all set up to communicate securely over their own VPN, which is what you get for free when you build this in Docker Compose. So I hope you like it. Um, in other videos, I will be talking more about what Docker Compose can do from volume and what you can use Docker Compose volumes for, so that you can actually have true runtime debugging, runtime updates. So when I write code, it automatically just builds and updates that site.